was home sitting and so to occasionally invest me with you. Yeah, he had somebody from Boson sound down. Yeah, talking about because the fear of extreme opposites like that is really scary. Yeah, it's
Center's kind of very close to land, and now I helped create a minor protocol. Interesting. It's really application.
Good evening. I'm so pleased to welcome all of you here to St. Michael for this beautiful event, this just wonderfully series that Zoe and the women of St. Michael has put together, Bridging the Gap. And today we'll be bridging the gap between science and faith. I have to say this is one of my favorite things to think about from a theological perspective. It started back, golly, probably when I was a little girl, thinking about what was happening as I read the book of creation and we look at the stars. And then when I got into seminary, there was a book that I read in one of my classes by Cynthia Crysdale called Creator, God, Evolving World. And I also had the benefit of being at Swanee at the same time that they had a resident physicist priest who was there. So it was it's really one of my, when I saw that this was one of the topics that the women of St. Michael's had chosen for their series, I was delighted. Because I believe that the study of creation draws us closer to God. I believe that our physics and science, they look at how things are created and how things work. And our Bible tells us why they were created. And we Episcopalians, we get this. As our infamous Episcopal theologian, also comedian, Robin Williams once said, we are happy to believe in both God and dinosaurs. And our prayer book reflects this rational, this thinking perspective as we think about and we pray through our faith. I mean, look at prayer C in our Eucharistic prayers. It's a prayer that we affectionately call the Star Wars prayer. And it says in it, God of all power, ruler of the universe, you are worthy of glory and praise. Glory to you forever and ever. At your command, all things came to be, the vast expanse of interstellar space, galaxies, suns, the planets in their courses, and this fragile earth, our island home. By your will they were created and have their being. From the primal elements you brought forth the human race and blessed us with memory, skill, and reason. And so I want to open this evening with another prayer from our Book of Common Prayer. It's prayer number 40. You'll find it in the back, and it's the prayer for knowledge of God's creation. So let us pray. Almighty and everlasting God, you made the universe with all its marvelous order, its atoms, worlds, and galaxies, and the infinite complexity of living creatures. Grant that as we probe the mysteries of your creation, we may come to know you more truly and more surely fulfill our role in your eternal purpose. In the name of Jesus Christ our Lord. Amen. I now invite Zoe Hart, the president of the Women of St. Michael's, to come and welcome you.
Thank you so much, Robin. Well, hello, everyone. I am Zoe Hurt, this year's president of the Women of St. Michael, and thank you all for coming out on this rainy night to our third event in the speaker series titled Bridging the Divide, in which we address some of the structural divides in America today and provide some hopeful solutions. Topics include today's talk on faith and science, the January Public and Private Community Partnerships with Peter Brodsky, our annual spring luncheon on April 24th with Ambassador Kay Bailey Hutchinson on politics, and our most recent talks on acculturation here in North Texas and public education in America. As many of you know, this topic was born out of my concern about the negative direction public discourse has taken in our country and my desire to help change in any small way the tenor of that discourse for the better. I would especially like to thank from the church our chaplain and associate for mission and outreach, the Reverend Robin Hinkle, Tish Wazinski, director of parish life, Nozar Darapayama, Director of Facilities, and Cedric Buard, Manager of AVL and Technologies. They are our unsung heroes for these speaker series. Additionally, from the Women of St. Michael, I would like to thank Monique Black, Reservations Chair, Amy Blackie and Christy Crenshaw, our speaker series catering chairs, and our programming chairs, Alison Bovard and Diana Newton. Without all of these people, this series would not be possible. This evening, we are very privileged to have with us Dr. Frederick Olness, PhD, Professor of Physics at SMU, to talk with us about faith, science, and deciphering the universe. As some of the slides he is going to show are quite detailed, Dr. Olness has generously agreed to allow us to share this presentation with the women of St. Michael so that you can review it at your leisure. So please look for this in the coming days. To introduce Professor Olness, please help me welcome Diana Newton, Women of St. Michael Programming Chair to the lectern. Diana is currently the director of the Tower Scholars Program and senior fellow at the John Goodwin Tower Center for Political Studies, where she lectures in the Public Policy and International Affairs minor at SMU. After Dr. Olness's talk, you will see there are some note cards in the back of your pews. So there will be a question and answer period, and please feel free to fill those out and we will come and collect your questions. And then after everything is finished, please join us in the parlor for wine and hors d'oeuvres. Diana?
Thank you so much, Zoe, for that wonderful introduction. Welcome to everyone who braved this iffy weather. I feel confident that it will be worth your wet travel to hear Dr. Frederick I. Olness tonight. He will give us his perspectives on faith, science, and deciphering the universe. I'd like to give you a brief introduction of this incredibly accomplished guest. I could go on for hours, truly, but Dr. Olness went to college at Duke University, where he graduated magna cum laude with distinction in physics. He went on to the University of Wisconsin at Madison, where he received his master's and PhD in theoretical particle physics with a minor in math. Fortunately for us, he decided to make his career at SMU in the physics department, where he is a professor of theoretical particle physics. While he is a brilliant scientist, he is also a man of faith, and we asked him to speak tonight about how faith and science can and do coexist. If you are like me and your physics career ended in high school, you may appreciate a little help understanding what theoretical particle physics actually is. According to the Google page I chose, which promised a definition with pictures, it is the study of coming up with mathematical explanations for natural events, and noted that some experts in this field are pondering some very complex problems and questions, such as how the universe developed. This is, in fact, what Dr. Olness is doing on and off campus. Off campus, Dr. Olness has been involved with various groups all over the world, trying to understand just how the universe is put together by colliding high-energy subatomic particles to better understand interactions and force among objects and deep structures of space and time. He has spent a sabbatical year at the CERN particle accelerator outside of Geneva, Switzerland, and continues to do research there with fellow scientists. CERN boasts the Large Hadron Collider, which is the world's largest and most powerful particle accelerator, where the Higgs Boson was discovered in 2012. He's also worked and researched at the University of Pittsburgh, Particle Physics, Astrophysics, and Cosmology Center, the Fermi Lab, affiliated with the University of Chicago and Illinois, the Electron ion collider that is being built at the National Brookhaven Lab, affiliated with the Department of Energy on Long Island, New York. He's also serving on the Department of Energy review panel to upgrade the solenoidal large intensity device at the Jefferson Laboratory in Newport News, Virginia. And he serves on the nominating committee for the American Physical Society's group on hadron physics. On campus, Dr. Olness has received many well-earned accolades as well. In addition to serving as president of the SMU Faculty Senate, which I'm just guessing is a thankless job, he has been awarded the Dedman Distinguished Professor Award, the University Distinguished Citizen Award, the SMU Ford Fellowship for Research, and the M Award, which is the most highly coveted recognition given in service to the university. given for service to the university. Beyond his ability to reach and inspire college students in the classroom, reflected by his receiving the Hope Award for teaching excellence more than once, Dr. Olness and his colleagues regularly put on an SMU circus for public school children throughout Dallas, where they entertain and engage the students with all sorts of tricks and experiments in physics. Trust me when I say their antics go way beyond the baking soda volcano of my childhood. They include, some of the things they do include breaking a slab resting on the stomach of Dr. Olness's colleague who was lying on a bed of nails using a sledgehammer. They also include using liquid nitrogen to fire metal rings into the air and a fire extinguisher to propel him across the classroom. You can imagine the delight of the school children. In short, he is a popular professor, an important member of the community, a serious scholar with 33 publications that have been referenced in other scientists' work more than 100 times, and 6 of those have been recited more than 500 times. This is an incredible accomplishment for a scholar, way more important and way cooler than being retweeted, just to give you some academic context. And we are lucky to have Dr. Olness's wife, Gloria Olness, who is also a doctor in her own right and a professor at UNT, with us tonight, and she is sharing her birthday with us. So let's... Thank you to Gloria, and thank you to Dr. Olness.
Thank you, and good evening, and thank you for that introduction. I think one of the things that drew me into physics was they had lots of good toys, as Diana just described, fire extinguishers and things like this. And when I was a kid, I was interested in taking things apart. I wasn't so good at putting them back together. Maybe that's why I'm a theorist, and they don't let me in the laboratory anymore. But anyway, so I like taking things apart. But now in my research, I take really small things apart, like atoms and nuclei and things like this. And so I'll tell you a little bit about some of that tonight. And this is sort of a fun topic because I get to share combine my passion with my profession. And so I've started here with a composite, which I think illustrates, in some sense, the compatibility and complementarity between faith and science. On the right, we have the creation of Adam by Michelangelo from the Sistine Chapel, and that's composited with the Crab Nebula on the left, where you have the creation of stars and things like this. And it really makes a beautiful image together, but they really do fit quite nicely together. And hopefully, those have been important elements in my life and my journey, and hopefully I can convey that to you across this evening. So to go ahead and get started, I'm going to begin. And let me start with a bit of an analogy to set things up. And we're going to go back in time a little bit. And a while back, there was a movie called The Truman Show with Jim Carrey. And in the movie, basically a TV show adopted a little baby, and then he grew up in the TV show. And he was confined to the TV show. It was a big studio, but everything he experienced was confined to the TV show. That was his reality. And it had boundaries, and everything was controlled by the producers. And so this was the world he lived in. He wasn't familiar with the world that we have. This was an artificial world inside the TV set. And sorry, spoiler alert, but at the end of the show, he discovers the boundaries of his universe in some sense, and that's illustrated there when his sailboat runs into the wall. And then he sort of walks up the steps, and he finds an exit to the studio. And as he's about to exit, he's addressed by the director of the TV show. And so he calls out his name, Truman. And Truman says, "Who are you?" And the answer is, "I am the creator," pause, "of a TV show." But I'm sure that choice of words was made very deliberately. They could have said, "I'm the director, I'm the producer." But no, I'm the creator, because he created this world that he lives in. And for Truman, this is his reality. He can only experience things within. Now, he has an exit door where he can go through the exit door and then experience things in the beyond and discover things in the beyond. That's wonderful. And the creator gives him the choice to stay or go. And of course, in the end, his curiosity drives him to go through the door to explore things outside of that. And when I think about science a little bit, this is in some ways the limitation we have. I can explore things that are within the visible universe. I can explore things at the small scales, at the large scales, but I don't have a door where I can go through and I go out to the great beyond. And I can't interview the creator and say, hey, how do you do this, or why do you do this, or something like that. So we don't have that ability. We can pray for wisdom, but I can't interview the creator like Mr. Truman did here. So there's a limit to what science can do. And so science is very good at addressing questions like how. How does something work? How does the nucleus work? How do the constellations work? Things like that. But questions of why are best relegated to areas of faith. Why? What is the meaning of life? Why are we here? Why does this? And that's sort of the separation in some sense. So there's a natural divide here, but the two fit together quite well. And so we'd like to take you on a tour of that. So we can't, unlike Mr. Truman, we can't interview the creator, and we can't go through that exit door to find out what lies outside our universe. So we're confined to inside the universe. So how can we find out about the creator with what we have? And as scientists, the best we can do is we can study the creation to learn about the creator. And so what we're going to do, and what we do in physics, is we're going to explore the universe at the most extreme distance scales, the large scale and the small scale. And that's illustrated in this set of figures right here. On the left, you have the pillars of creation. This is a new image from the James Webb Telescope. The James Webb Telescope, that's a successor to the Hubble. It took us 20 years to build that, and that was launched last Christmas, on Christmas Day, a very nice Christmas present from NASA for us. And it's been generating some absolutely incredible pictures of the universe. So this is the pillars of creation, the Eagle Nebula in our Milky Way galaxy. This is about 6,000 light years away. And inside there you have stars being created, stars being destroyed, supernovas, all sorts of things going on there. And we have this detailed picture that we can study things at the largest scale. And now let's go to the smallest scale, which is where I work with. I like taking things apart. This is an image of the atomic nucleus. And you see the electrons are represented flying around the outside. And in the middle, you've got a clump of protons and neutrons. And so we can study things on this distance scale. And again, thanks to the invention of both the telescope and the microscope, we can actually go at these extreme distances. Now, something that's particularly interesting about this, I work on the things on the right at very small scales, but a couple doors down from me over at SMU, my colleagues are working on the things on the left at the largest distance scales. Now, how is it that we're working on such different things, but we're in the same department? And the answer is very intriguing. The answer is that the laws of nature that affect the things at the small scale are exactly the same as what affects the things in the large scale. They're universal. They go from large to small. And so when I'm studying forces and interactions down here at subatomic scales, and people are studying forces and interactions at cosmological scales, those are the exact same forces. And I think that has a special elegance to it. And the way the universe was created, that is particularly intriguing. And I think this is in part what prompted Einstein to say the quote at the bottom, "The most incomprehensible thing about the universe is that it's comprehensible." And so I find that fascinating. So in my view, the universe is elegant, efficient, and intricate. And the deeper we look, the more ingenious is the structure. And I think Carl Sagan, the astronomer, said it quite nicely, so I'll go ahead and read this quote from him. He says, "Science is not only compatible with spirituality, it is a profound source of spirituality. When we recognize our place in an immensity of light years and the passage of ages, when we grasp the intricacy, beauty, and subtlety of life,
then that soaring feeling, that sense of elation and humility combined, is surely spiritual. And so when I look out there and I look at the largest things and the smallest things and think there's a uniform structure to that, the person who created that must have been terribly brilliant. That's far above what humans can put together. And so let me illustrate that. And if you had a bunch of humans getting together and say, okay, let's build a universe, see if we can do better. Obviously, what we do is we'd set up committees. You're probably familiar with being on committees and how successful they are. And so if the universe was designed by committee, we'd have a committee for the large-scale stuff and a committee for the small-scale stuff. And then one would use metric, and the other would use British units. And then when you try to put them together, they wouldn't quite match. And that's kind of illustrated with that picture on the left there. It's close, but not good enough. And so that's what happens when you mix units. But to err is to human, and that's natural. And we make errors. So mixing units, for example, when the Mars orbiter comes in and crashes into Mars because we messed up the conversion between metric and British, or when a passenger jet is flying across Canada and runs out of fuel because we measured the fuel in pounds instead of kilograms, mistakes happen. Another example on the left, on the right here is this cartoon. Oh wait, okay, I see what the problem is now. It's the architect's fault. And so when you have a committee, sometimes things don't quite work out the way you expect. And if the universe was designed by committee, these are the kind of problems you'd expect. But the fact that, and I'll say it again, the laws of nature are universal and apply at both the largest and smallest distance scales, I think that's miraculous. That's incredible. And the way it was set up, that's far beyond what any human, the fact that we can comprehend it is incredible. The fact that we could create it is certainly beyond us. And if you go back to the example of Newton and watching the apple fall from the apple tree, that was at the beginning of the scientific revolution. And what Newton realized is when he saw that apple fall from the apple tree, he realized that the gravitational force pulling that apple down was the same gravitational force that made the Earth go around the sun. And the fact that the laws of nature were the same at the human scale of Newton and the apple and the same at the cosmological scale of the Earth going around the sun, that unity, that unification was the beginning of his whole theory of gravity and the beginning of the scientific revolution, which got us to where we are today, which gives us this incredible scientific view of the world. So let me give you a brief tour of the universe, and we're going to go to the small scale because we're have limited time, and also that's the direction that I study. But if we were to go to the large scale, that's also very interesting, and I think some of the intricacy would also show up there. But I'm just going to go to the small scale and take a look at one example of how intricate and elegant things are put together. So we're going to explore the universe at the smallest distance scale, and but throughout, I'm sort of inspired by this quote of C.S. Lewis that, in this tour, I think you'll see that the fingerprint of God is on this. And C.S. Lewis says, "We may ignore, but we can nowhere evade the presence of God. The world is crowded with him. He walks everywhere incognito." And so let's take a look and see where we get. And so let's start out, we'll ask some age-old questions that physicists ask. So we want to figure out what the fundamental structure of the universe is. And we ask, okay, what are the fundamental constituents that everything else is built up of? How do they interact? What holds them together? Will the Cowboys make the playoffs? We discuss that some too. If anybody has some insights on these, especially the last one, see me afterwards, please. But anyway, this is the goal. We want to take things apart and figure out what things are made of. So let's go back in time a little bit. And back when my grandfather was in school, this is what the periodic table of the elements looked like. Nice and simple. So you had air, water, fire, and earth. 4 elements, very simple, very compact. And as I note over here, this theory, it's compact, it's easy to remember, and it fits on a T-shirt. And I think there's an unwritten law that if a theory doesn't fit on a T-shirt, it can't be fundamental. If it's too big for a coffee cup or T-shirt, no go. All right, so that's nice and simple. But let's go a little bit earlier, fast forward to when my dad was in school. And so about 1900, instead of those 4 elements, we're now up to 103. Wow, boy, that's a lot. And you probably remember something like this from back when you were in chemistry class. So 103 elements, and memorizing them is difficult. Fortunately, Tom Lear wrote a song with all of them in them. But anyway, yeah. So this is quite a bit different. And so let's check off the elements. This is complex. It's difficult to remember, and the bottom line, I think the killer, it's hard to fit in a T-shirt. So that can't be a fundamental theory. And in fact, when we see this repetition, this 103 atomic things, atomic is supposed to be indivisible. That means it's the smallest thing. It can't be divided into something smaller. But 103 fundamental things, that's a big number. And so it was a little bit after 1900, we discovered, in fact, you could take the atom apart. And that you could take it apart, that's made up of electron cloud around it, and then the nucleus was a bunch of protons and neutrons. And so with those 3 things, you could take protons and neutrons, build up a nucleus, sprinkle some electrons around it, and you had the atom. And you can build up all 103 elements of those 3 fundamental things. And so then underneath we had something more fundamental. Now, that worked pretty well until about the mid-20th century, when we discovered that the protons and neutrons had cousins and relatives and step-cousins and all sorts of other things. And so we discovered the protons and neutrons themselves are composite. They're made up of smaller things. And it turns out that they're made up of quarks. And so let's fast forward now to 2022, and here's our periodic table. And I can make up everything in the universe with these 12 building blocks. There are 6 quarks and 6 leptons. The electron, for example, we've seen that before. That's one of our leptons. And then I've got the up quark and the down quark and a few others. And just by putting these together, I can build up everything I see in the universe. So, for example, I can mix the up and down quarks together. I can make protons and neutrons. I can use that to make atomic nuclei, sprinkle on the electrons. I've got atoms. And then I can make elements. And then I can make cups, plates, buildings, bricks, all sorts of things out of just these 12 things. So it's very fundamental. Let's take a look at what the thinker's thinking here. He says, so everything is made of quarks and leptons, eh? Who would have thought it was so simple? And that's a very nice picture. Go to our checklist. It's compact, easy to remember, and it fits on a T-shirt, so it's a candidate for a fundamental theory. That's great. So it seems like we're done. We can pack up a lab, go home, go do something else, pick up a hobby. But not quite. There's still, as simple and elegant as this is, there still are a few loose ends that we have to tie up. And the first one of these is I've put these 12 building blocks into 3 columns, and these are called generations. And something that's rather strange about this is everything I observe in the world, I can actually make with this first column. I don't need the second column or the third column. And so now you start wondering, when we saw this repetition before, back with 103 elements, that was a clue that there was something underneath more fundamental than what we're looking at. So now I look at this and say, wait a minute, why do I need 3 copies? Is that telling us that underneath there's something even more fundamental? We don't know. That's one of the things we're looking at the Large Hadron Collider over in Geneva and the future one that I'll talk about in a moment. So that's one unsolved question. But another one, and the one I'm going to talk about tonight, is how do they acquire mass? Okay, we know things have mass. You pick up water, that has mass. You pick up a brick, that has mass. So if these are the building blocks that we're building everything out of the universe, it has to have mass. But it turns out there's a puzzle. There's a problem. And this is a problem we discovered about 50 years ago. How do the quarks and leptons get mass? And as a theorist, I would just sit down and I would say, okay, I'll write down a mass term and put it in the theory, and we're all set. But without going into too much detail, it turns out that apparently when you just add mass into the theory, it spoils a fundamental symmetry. And again, without going into too much detail, 100 years ago, Einstein taught us that symmetries are important. He used symmetries in his special theory of relativity to deduce that, which is one of the foundations of our current framework. And for example, specifically his special relativity, the two inputs, the symmetries, are that all reference frames are created equal, and light travels with a constant speed c in all reference frames. So those two symmetries give us special relativity, which has been proven many times over. So Einstein told us we want to respect symmetries, but we have to give quarks mass because we know things like this have mass. So we have a puzzle. We have an apparent contradiction. And, as humans, we try to figure that out, but, we're stuck. Now, at this point, you might be tempted to invoke what's illustrated in this central comic here. It says, I think you should be more explicit here in step 2. And in between all this algebra, there's a little phrase, then a miracle occurs. And so, we might be tempted to throw up our hands and say, okay, we're stuck. We don't see how it works. We need a patch, or we need a miracle, or we need something else. But just because humans can't figure it out doesn't mean God hasn't already figured out a very intricate, clever way that obeys all the symmetries and even more. And it took us 50 years to figure this out. There's some things we figure out very quickly, some things we figure out in 50 years, and maybe some things we may never figure out. Depends on the wisdom we're granted. But there was a proposal that a way to fix this was the Higgs boson. So enter the Higgs boson, and you may have heard about this. There's all sorts of articles and books in the literature. Here's one of the books you can find. This is Leon Letterman, the former director of the Fermilab facility. And this is, the title is The God Particle. I cringe a little bit when I see the title. The Higgs is very important, but I think the choice of God particle might have been more to sell books than, but anyway. There are lots of things in the literature about it. But the Higgs boson was proposed as a solution to this, to solve the problem of the symmetry in the mass. So can it solve the problem? And let me illustrate this for you. And I'm going to need some help. I'm going to need the help of two very well-known scientists, Calvin and Hobbes, which you're probably familiar with. So scientists Calvin and Hobbes. And you see, in fact, they are testing one of Einstein's theories. The idea is that the faster we go, the slower time goes. And then Hobbes says, gotcha, it's 10:23. But they're also testing out Newton's second law. And here's Newton's second law. It says that force is proportional to mass times acceleration. So in this case, Hobbes is exerting a force on the wagon, and he can measure an acceleration, and from that he can deduce a mass. Wonderful. So that works out, but let's redo this experiment, but this time let's do it underwater. Okay? And so they're doing it underwater, and you know what happens underwater. When you move something around underwater, the water exerts a drag on the object. Okay, so now we repeat the experiment. Hobbes exerts the same force, but he gets a different acceleration, and so it appears the object has more mass. So because of the drag on the wagon in the water, it appears to be more massive. And this is exactly how the Higgs boson mechanism works. So the postulate is that the Higgs boson permeates all of space, and the quarks and leptons, as they move through the space, the Higgs boson will drag on them. Some of them will drag on more, those will be heavier. Some will be less, those will be lighter. And the Higgs boson drags on them, and this generates the mass. And so this proposal, it's ingenious because the Higgs boson generates the mass, but without spoiling the symmetry that Einstein told us was so important. That's fabulous, absolutely ingenious. It took us 50 years to figure that out and come to this point. But that's a great idea, but you really want to test this, okay? I mean, yeah, so you drag things through the Higgs field and they have mass, but if the Higgs field is all around and dragging on things, you ought to be able to make Higgs bosons themselves. Well, it turns out it's hard to do, but in fact, we have done it, and that's what we did over at the Large Hadron Collider over in Geneva, Switzerland, at the CERN lab. Now, how do you do it? Well, here's the recipe. You take 18 miles of tunnel and 1,000 plus magnets, 10,000 plus scientists, collide protons and protons, make a Higgs, and go collect your Nobel Prize. Sounds easy. There are a few details I left out. Here's an overview of the CERN facility. So here's the tunnel, 18 miles around. The actual tunnel is anywhere from 100 meters to 300 meters underground. You've got Lake Geneva up here. Here's the Geneva Airport. Downtown Geneva is off to the right. Here's the Jura Mountains in the French side. The French-Swiss border goes right down the middle. And so this is where they did it. And so after you make them, you have to see them to make sure you discovered it. And so you need a detector, and here's the Atlas detector. And to scale, here is the size of a person. So this is a huge thing. Turns out you need really big detectors to measure small stuff, but oh well. This is about 60 feet high, 100 feet wide. It's bigger than this entire room. It would not fit in this entire room. But that's what it takes to go and do that. And sure enough, they found this. And on July 4th, an easy date for Americans to remember, July 4th, 2012, they announced the discovery of the Higgs boson, and it won the Physics Nobel Prize the next year in 2013. But this was a remarkable 50-year journey that it took us. But, and again, I've given you just one example, but why do I think the universe is elegant, efficient, and intricate? Because it took us 50 years to figure out the Higgs boson. And again, we came to it initially and said, oh, there's no way. You can't put mass in, it'll spoil the symmetry. But there was a way, okay? It took us a while to figure that out. It took us some very clever people. But in the end, it was elegant, it was intricate. And there are many other examples like this. The deeper we look into how things are put together, the more ingenious is the structure. And so looking at this, how ingenious that's done tells us something about by looking at the creation, it tells us something we can infer about the Creator and the scope of his wisdom. Hence this quote from Romans, "Oh, the depth of the riches both of the wisdom and knowledge of God. How unsearchable are his judgments and unfathomable his ways." So revelations of the creation yield revelations of the Creator. And as scientists, that's all we have. But you see things like this and you're just awed that it's put together so intricately. And the fact that we can figure it out, sometimes it takes us 50 years, but the fact that we can figure it out is, as Einstein said, incomprehensible. So again, I've just given you a glimpse at the small scale. There are equal examples at the large scale of this. And as I say here, the laws of nature hold both at the largest and smallest scales. For me, that's the thing that's most incredible. It's not that God says, okay, there's one set of laws down here, and then I had to patch it up and do something different here. The same forces I'm studying down here are what my colleagues are studying up here. One set of natural laws from one scale to the other. That's elegant. That's intricate. That's beautiful. And again, Einstein says the most incomprehensible thing about the universe is that it's comprehensible. So that's the present. And in one slide, let me tell you a little bit about what the future holds. So we have over in Geneva, we have the Large Hadron Collider, which collides protons and protons that I talked about. But now we're going to build something new in the US, specifically on Long Island, New York, and we're going to build the Electron-Ion Collider. And this will collide beams of electrons into beams of nuclei and allow us to explore the innermost nuclear interactions and really look at the details of those detailed interactions. So this is an aerial view of Brookhaven National Laboratory on Long Island, and this is the future EIC ring. It's about 2.5 miles around. And they'll get nuclei going in one direction, nuclei going in one direction, electrons in the other, and then collide those. And again, you need detectors to look at what comes off. So you'll have detectors that sort of look like this. This is the star example, a star collider detector just as an example. But you'll have large detectors like this, and then there'll be a spray of particles given by this superimposed image, something like this. And using this, we can look in detail at the nuclear interactions. And maybe we can answer questions about, are there 3 generations necessary? What about the nuclear forces? What about the strong interaction? Other things like that, and explore other things. And I have to mention, I got some very good news just today, in fact, that collaboration of us based at Brookhaven Lab, about 20 institutions, put together a proposal, and we just got approved to have a topical collaboration working on this. So I will be spending the next few years in part at the lab and working with them on that. So this is what I'm going to be doing in the future, but it's going to be a lot of fun. Again, looking at the smallest things in nature and to see what's going on there. And I think we'll have journeys that are equally fascinating that we have with the Higgs. So let me go ahead and finish where I started, again with this composite, because I really think it shows both the complementarity and the compatibility between faith and science. And I also will finish with this quote from William Bragg. William Bragg invented Bragg scattering, which is one of the techniques we use for diffraction of crystals and do crystallography to get the structure of crystals. And in fact, he advised and mentored Crick Watson and Rosalind Franklin, who deciphered the helix structure, the double helix structure of DNA. So I think it's very fitting. He was certainly very influential on the science side, but I think this quote really sums it up quite nicely. He said, from religion comes a man's purpose, from science, his power to achieve it. And very succinctly, I think that says it all, and so I'll go ahead and finish there. So thank you for your attention. Thank you for joining us.
Fascinating and whirlwind, but you did it so well and explained so much, and we're so grateful. I'm going to ask Allison and Zoe to collect any cards that are out there if you're working on questions and bring those up to me, but I have a few to begin with. So one question, do the natural laws hold up as you get closer to the moment of creation, Big Bang?
That's a hard one, and that deals with more the cosmology and the astrophysics side of it. But there's a point at which our current theories break down. And for example, gravity. Well, you jump off a step or something like that. Gravity feels really strong, but it's actually quite weak. But when you get to very small distances, and sort of you run the time backwards, you get to the point where our theories begin to break down. And so we don't have an answer to that. That's a question where you almost have to go to the great beyond and sort of come at it from the other side. So there are limits to what our theories can currently do. And
do you anticipate at the EIC that you will gain more knowledge about those kinds of smaller things?
We're going to be looking at, it's a strong interaction that holds nuclei together, and we're going to be looking at that at short distances, but that still may not be enough. That may get us farther back, but there's still going to be a limit where things just break down as you sort of run the clock backwards.
Great, thank you. Why wasn't the Conductor Collider project in Waxahachie successful? It would have improved your commuting time.
I was very sorry to see that go, and I was here for part of the time the SSC was here down in Waxahachie, and it was certainly exciting because we had all sorts of people coming through. I'd teach my class in the morning, go down in the afternoon, and on the way to the cafeteria, I'd walk past 2 Nobel laureates and 3 lab directors. But it didn't work out, so CERN did it over in Geneva. They were successful, and Geneva is a nice place, but it's a long plane flight. But I'm looking forward now. We are building a facility here in the U.S., and it's again, CERN is doing protons on protons. We're going to do electrons and nuclei. And so basically, electrons, as far as we know, are completely point-like. They're not, they don't decompose into anything else. So that gives us a very, very good probe to really look at the nucleus in detail. And so we're going to have a lot of data to sift through We may have to use some new techniques. Things like artificial intelligence and machine learning are starting to play a larger role in some of the analyses, so we're doing that, and also the advances of computing. Many of these calculations, the analysis of the Higgs boson, we could not have done without the computer power that we have now. If we tried that a decade or two ago, we could not have done that.
Right.
So I'm looking forward to that. I was sorry to see the SSC go, but I'm glad for CERN, and I'm even more glad that we will have a facility here in the U.S. in the future.
This is a follow-up question from someone else, but why Long Island? It seems small and cramped, and so does Switzerland. So is there any rhyme to that reason?
So they had a competition for where to put the machine, and you need a ring. Basically, you need a nuclear beam and an electron beam. And so Brookhaven already had the nuclear beam, and Jefferson Lab in Virginia already had the electron beam. So those were the two competitions, and basically you had half the machine in one place, half the machine in the other. So the competition was limited to those two choices, because then you only have to build half the machine. And ultimately, it was a tough choice between Virginia and New York, but in the end they decided to go with Brookhaven. They had the nuclear beam, so all they have to do is add the electron beam, whereas in Virginia they had the electron beam, they would have had to do the nuclear beam. So that's the logistics of how it happened.
Great. Okay. So recently, this is another follow-up question from someone else. I've recently been reading about or hearing about quantum computers. Do you believe scientists are close to making them work? And if yes, what would be the implications?
Yeah, that really changes the field, because our computers right now are limited to bits 1 and 2. We're working in binary. And if you can do quantum computers, that tremendously opens up things. One example they often point to is encryption and factoring prime numbers. Right now, all our banking encryption, things like that over the internet, depends on the fact that we can't factor prime numbers quickly. But with a quantum computer, that would be able to do, that would become almost trivial with something like that. And so that gives you an idea of how powerful these are. The hard part is you have to maintain a quantum state over a number of operations. So you have to maintain a coherent quantum state while you're doing the calculations. And so that's the challenge, because all sorts of things can interrupt that. For example, you have cosmic rays from the upper atmosphere coming down, and in computers that can give you a bit flip. At a normal computer, we have parity to check that, but in quantum computers, if you have cosmic rays coming down and causing decoherence of your quantum state, that would spoil the game. So they're working on that, but that's a very new field, and it's very promising if they can get over those hurdles.
Okay, great. You indicated the laws of nature are identical at a very large level and a very small level. How does this relate to the search for a grand unified theory?
Okay. So I didn't go into detail, but the laws of nature, currently we have four forces. We have gravity, the strong, weak, and electromagnetic force. So those are the four forces. And actually, of those, gravity is the hardest to unify. And there's some ideas about that. String theory, in particular, has given us some ideas about that, but we haven't fully done that. And the other challenging part is you want to be able to test it, just like we tested the Higgs boson. And the problem is most of these theories unify at very high scales. So testing them is particularly difficult. But we have made some progress, particularly with the original unification was electricity and magnetism. That was done by James Clerk Maxwell back in 1860. And so now, and then we have some theories that unify that with the strong and weak force. But so gravity is the hard one, because even though we're most familiar with it, that comparatively, compared to the other forces, that has a very different character and is much harder to unify. So string theory is trying there, but that's still an unsolved one.
Okay, great, because that was another person said, is string theory dead? If so, what is the next best theory that connects large and small?
It's tough because string theory is very promising in terms of unifying things, but the predictions are all at very high scales. And the difficulty is, the Large Hadron Collider is 18 miles around. We've got the EIC at, 2.5 miles. How big, there's a limit to how big we can make it. And that means there's a limit to how much energy we can do it. So we can infer, we can do some things indirectly, but we may have to find different ways of attacking that, because currently the predictions are all at scales much higher than our experimental reach.
Okay. Do you imagine anything smaller than quarks and leptons, and who gets to decide those names?
So if you postulate it, you get to decide the name. For example, the name quark was coined by Murray Gell-Mann in the 60s, and I believe there was a mention in Finnegan's Wake somewhere. So I don't, I guess he thought it was a nice word, and it wasn't being used for something else, so that's where it came from. But if you discover them, you get to name them. And there are some theories about things underneath quarks and leptons. There's one theory where they call them preons. So pre mean before, and then on, putting that together. So there are various theories of preons. But again, those are happening at scales beyond what we can do. So, biology happens about 10 to the minus 5 meters. Chemistry happens about 10 to the minus 10 meters. We call that an angstrom. Particle physics is about 10 to the minus 15 meters. That's the size of a proton. We're down about 10 to the minus 18, 19 meters now. And as far as we can tell, the quarks are, indivisible. The electrons are indivisible. But if we go smaller, we might find that they decompose. Okay. And so we'll have to see. But there are theories looking at that. And again, the idea is to solve the problem of the generations. Mm-hmm. Why are there 3 generations? We don't have a good answer to that.
Mm-hmm. I'm going to ask you a question a little bit about your classroom. You teach at SMU, you have for many years. You're married to a professor who's also in the classroom. Are you noting a change in the level of curiosity among your students? Are you finding students are less interested in science and more interested in going down rabbit holes on social media? Or since you're at SMU, which is a fabulous institution, that's not the case? Are you seeing anything in that regard in terms of science?
Maybe I'm not seeing a representative sample, but for many years, in fact, I taught the music and physics course, mm-hmm. and there was really fascinating. We have a fabulous music program over there, but those students are really curious, and what we did there, we taught them a little bit of the physics of their instruments so they could play it more, and that really sparked their curiosity, and they really got into it. And but I think that goes over to the other courses I teach. Mm-hmm. Once they kind of see what's going on, it sparks their curiosity, and then they want more. So maybe I have a not a normal sample. But,
we can have faith.
I've been very fortunate. The students, we've got some very curious students over there.
Yeah. Great. I'm glad to hear that. So one person has asked, we often speculate on the infinity of the universe at the macro level. Clearly, infinity goes in the micro level as well. Do you think that funding for research in particle physics would be greater if the public had a better grasp of the infinite extension in the micro direction?
There are many facets to that question. I think scientists can and should do a better job of sort of explaining what they do and why it's important and relevant. Things like basic research, it's sort of hard because there's no direct application, mm-hmm. but things that have come out of the field of particle physics, superconducting magnets. When we built the Fermilab machine, That was 4 miles of superconducting magnets. That was the most superconducting that had been made. But that set the stage for things like MRIs, which you have now in shopping malls and all over. So that kind of technology goes out there. So I think we should do a better job of communicating that. But certainly there has to be a balance. You need some basic research, you need some applied research, and you have to find a balance of that. For us, we've been fortunate because one of the best things for us is a relatively steady state. And that means you can take on long-term projects like the Large Hadron Collider, the EIC. That takes many years of planning, developing, things like that. So for us, uniform funding and commitment to a project. You always have to compete, so we have to make choices. Right. Resources are finite, but once we do it, then if we follow through with it, and that's important. And
would you say in your field right now there's a real interest in funding these kinds of things because there have been so many successful discoveries?
It's been relatively. I think we've recently kept up with inflation, so that's good. And I have to compliment. When they planned the Electron Ion Collider, the SSC failed for a number of reasons, and maybe some of the people didn't make the best choices in terms of understanding how the funding works. But when they set up the Electron Ion Collider, one of the things they did was they went to the Department of Energy and said, okay, we're building the EFRB facility right now, and that will be finished in this year. So what we propose is we take that construction money and then we put it on the EIC. And so instead of going and having them go to Congress and say, hey, we got a new project, we need new money, right. They just said, okay, this is a priority, we're going to finish this, and then we're going to start this. Okay. And so that sort of planning, they thought very carefully about it, not only the physics, but how you fund it with limited resources. And I think that's one of the reasons it was successful.
Great. Okay, well, I'm going to conclude with one last question, which is, if we're interested in learning about this intersection of faith and science, are there any books that you would recommend? Should we let you get back to us on that?
Yeah, that's hard. I mean, there are a variety of things on the Higgs Boson. There are a variety of things on the applications. There's probably not so much on the interface. Mm-hmm. And I think that's a place where there could be more. So off the top of my head, I can't think of something, but
maybe
again,
you'll,
if somebody has a
author that book.
Yeah.
Maybe you'll author that book after your time at EIC. Let's thank Dr. Olness.
Thank you very much. Appreciate it.